Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, my name is Arifatul Soliha and my friend Griselda Clevery Miwaji. Now we're excited to share with you about image segmentation and IOU evaluation for retinal optic disc detection using morphological processing and thresholding techniques. Before we begin, let me guide you through the key points we'll be covering in this presentation. There are introduction, methodology, programming code, result and discussion, and lastly, conclusion.
Okay, we will start with a brief background to provide context for our topic. First, we need to understand what retinal optic disc is. The retinal optic disc, or optic nerve head, is a circular area at the back of the eye where the optic nerve fibers exit the retina and travel to the brain. The optic disc serves as the convergence point for the axons of ganglion cells to form the optic nerve, which transmits visual information from the retina to the brain. In medical imaging, the optic disc is often segmented and analyzed in retinal images to detect abnormalities, calculate the cup to disc ratio, and monitor disease progression. However, retinal optic disc imaging poses a challenge due to the difficulty in distinguishing optic disc area from the other retinal structures, such as blood vessels, surrounding tissues, and retinal background. Thus, it is essential to employ an appropriate method to ensure that the image can be easily identified.
Next, we will discuss the methodology of our programming approach. In this project, we utilized four key programming methodologies to process and analyze the image effectively. There are Gaussian blur, grayscale conversion, thresholding, and morphological operation. Okay, first let's discuss Gaussian blur. Gaussian blur is a fundamental method in image processing used to smooth image by reducing noise and fine details. It works by applying a Gaussian filter, which is based on the Gaussian function. This creates a Gaussian distribution that determines how the surrounding pixel values contribute to the final output for each pixel. And programming Gaussian blur is implemented using the function cv2.gaussian blur in OpenCV. The level of blur is determined by the standard deviation provided as a parameter. A higher standard deviation creates a more blurred effect.
Next, let's discuss the grayscale conversion method. The grayscale conversion method transforms a color image into a grayscale image. A grayscale image only represents one intensity value per pixel. Here's how this method works. First, it takes three main colors components of the image, which are red, green, and blue, or RGB. To convert the image into grayscale, the luminance intensity is calculated using formula which is gray equals to 0.299R plus 0.587G plus 0.114B. After calculating the grayscale intensity, the values of R, G, and B are replaced with the grayscale value for each pixel. The result is an image that only contains varying shades of gray without any color. In programming, grayscale conversion is implemented using the function cv2.cvtcolor with parameter cv2.color underscore bgr to gray.
Okay, next is the thresholding method. This method converts a grayscale image into a binary or black and white image. As its functionality, the thresholding method assigns a value of 0 opaque to all pixels with grayscale intensities below the threshold value. Meanwhile, all pixels with grayscale intensities greater than or equal to the threshold are assigned the maximum value or weight. To determine the appropriate threshold value t, an analysis of the image histogram must be performed. This involves identifying the peaks and valleys in the histogram. The grayscale value at the deepest valley between two peaks is selected as the threshold t, ensuring an effective separation of regions in the image. In programming, threshold is implemented using the function cv2.threshold.
The final method is morphological operations. Morphology is a technique or process used for image processing based on principles of mathematical morphology. There are three basic operations in morphological processing, which are AND, OR, and NOT operations. The output of the NOT gate is the inverse of the original image. The output of the AND gate is the intersection of the original image. Lastly, the output of the OR gate is the union of the original image. In this program, we utilize the closing operation, which is a morphological process that combines dilation followed by erosion. This method effectively closes gaps or holes within objects while preserving the original shape. Before that, let me explain the types of morphological operations available. First up, we have erosion. It reduces object size by removing pixels from the edges. Using a kernel, it replaces the center pixel within the minimum value under the kernel. As a result, object shrinks, especially if any pixels under the kernel doesn't match, while dilation enlarges objects by adding pixels to their edges. The kernel sets the center pixel to the maximum value under it, making objects expand outward. Opening combine erosion followed by dilation. This sequence removes small noise during erosion, and dilation restores the main object without bringing back the noise. Lastly, closing is the reverse of opening, starting with dilation followed by erosion. It fills small gaps or holes within objects, keeping the gaps closed after shrinking the edges back. In this programming project, we selected the closing method after comparing the four available morphological operations. Erosion is used to reduce the size of the object, remove small noise, and separate connected objects. Dilation is employed to enlarge object, fill gaps within objects, and connect separated objects. Opening is effective in removing small noise such as isolated dots or small objects while preserving the shape of larger objects. Meanwhile, closing, on the other hand, fill holes or gaps within objects and connect separated objects. Based on these characteristics, we concluded that the closing method is most suitable for processing our image.
Next, we will discuss the section of imaging code. Before that, we will present the algorithm of our program. It begins with load dataset, read image and corresponding ground truth mesh, followed by applying Gaussian filter, convert to grayscale, apply thresholding, apply morphological closing, calculate IOU, and save the result. After processing its image, the program will repeat the steps for all images until completion. The program begins by importing the necessary libraries, including CV2, NumPy, OS, and matplotlib.pyplot. These libraries provide essential functions for image processing, array manipulation, file handling, and visualization of image. Next up, we need to load the dataset folder. We obtain the data from the Google Drive link given by Papanega. As you can see here, we chose Retinal Optic Disc topic. There are two important dataset folders to keep in mind, which are image folder and mask folder. Image folder contains the original image of the Retinal Optic Disc, while the mask folder contains the corresponding mask. Next, we define the function used in the program. This is done to ensure that the code is reusable, concise, organized, and efficient. By using function, we can easily apply the same operation to different images without repeating the same code, thus optimizing the process. In image processing, the code is developed based on the chosen methods. First, the image is read, then the Gaussian blur method is applied to smooth the image. Next, the image is converted to grayscale. Afterward, the image undergoes thresholding, followed by the application to the morphological closing method. Finally, the output of the program is compared with the exciting mass using the IOU or intersection over union code to generate a score that reflects the accuracy level of the result.
Then we will visualize the results of the program using the following code. Finally, we will save all the results using the following program. Next, we will display the result of the program and discuss them. Here are some examples of the results from our program. First, we have an image with an IOU value of 0.2423, followed by an image with an IOU of 0.4532, then an image with an IOU of 0.7246, and finally an image with an IOU of 0.8486. It can be observed that as the IOU increases, the accuracy of the predicted mask compared to the existing mask data also improves, and vice versa. From the programming results, 20 IOU data points were obtained randomly. Based on this data, a diagram was created to show the frequency of IOU values across 4 ranges. There were 7 data points with IOU values between 0.25 till 0.5 and 0 till 0.25. Meanwhile, there were 4 data points with IOU values between 0.5 until 0.75 and 2 data points with IOU values between 0.75 until 1. Additionally, the average IOU across all data points was calculated to be 0.369245. This value is considered not too bad, but it certainly needs improvement. We hypothesized that the IOU value could be improved by using an edge detection method in our program. This is because edge detection will emphasize the boundary regions, preventing them from being erased during image processing.
Last is conclusion. The methods used in this programming are Gaussian blur, grayscale conversion, thresholding, and morphological operation closing. The average IOU achieved is 0.369245, with the best result found in image 33 and the worst result in image 37. The suboptimal IOU performance can be improved by utilizing the edge detection method.
Thank you for your time and attention. We hope that the insights shared in this presentation have provided a deeper understanding of methodologies and approaches applied in our project. Should you have any further questions, thoughts, or inputs regarding this project, we are more than happy to discuss them. You can always reach us by WhatsApp or email. Once again, thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.